perform the classification of doubly beams. So once we are given with the section, reinforcement details, material grades are known, we can determine the row of the cross section. Then can I evaluate without going into detailed analysis that this doubly beam is tension controlled under reinforced doubly beam, or transition reinforced doubly beam, or over reinforced doubly beam. So when I'm talking about uh, these type of doubly beams, I am silent about the compression steel, because compression steel yielding or non-yielding does not affect the ductile behavior or the tension steel strains. So the classification will still depend upon the status of tension steel. That's tension steel, if its strain will be above 0.005, it will be excessively yielded, it will be tension controlled under reinforced. If it will be in between 0.005 and epsilon y, it will be in transition. And if the tension steel will be below yielding, it will be unacceptable over reinforced doubly beam. So for design, we are not putting the doubly beam in that over reinforced domain. And as well as in doubly beam, we have a second challenge to judge what is the strain or the stress in the compression steel. If compression steel is yielded when beam will fail, it will become case 1. If compression steel is not yielded when beam will fail, it will become case 2. So in classification with row, we also want one row equation which will tell us that whether it is case 1 doubly beam or case 2 doubly beam, so that without going into comprehensive review, just looking at the row and comparing it with some typical row which will tell us that compression will be at yield or it will not yield, will be very useful. So that is what I'm going to discuss today. 3 different row values: row max of doubly, row balanced of doubly, and row CY. We are using a subscript CY, compression yield, row CY for doubly. So I will judge that if my row is greater than that, my compression steel will yield. If my row will be less than that row CY, compression steel will not yield. So in this way, different cases we can judge and we can do the classification. Idea is derivations are very simple, almost similar to your singly beams derivations. Only thing different is now on the compression side, we have one more component, and that is compression force developed by the compression steel. So our longitudinal equilibrium equation sigma fx at section gives us T equal to C, and C actually has two components, CC plus CS. So I will substitute for T ASFY, and I am working on a condition that my tension steel is at yield or above yield, and also in calculating CS, compression force developed by the compression steel. I'm using AS prime for that compression bars area, and I'm assuming that compression steel is also at yield when I'm writing this equilibrium equation. And CC is just like in singly beams, we have the compression force developed by the concrete, and we are using Whitney's uniform stress on the area A into B. So this will give us CC. I will divide both sides of the equation with FY BD. So when I divide them, I will get cancellation of Fy, and since I am assuming compression steel at yield, I will also get cancellation of Fy over here, and also I will get cancellation of B in the first component after equality. So when I will replace AS over BD with rho on the left hand side, AS prime over BD will be replaced with rho prime on the right hand side. And I will rearrange the terms, and the first component is giving me A over D. Now keep focusing on this A. In all our derivations on next slide, this A will decide that what row I am going to derive, which row I am going to derive. Now I will put A of my choice. For example, I have a strain diagram on the right hand side. You are well familiar with the linear strain diagram. The only thing different is now on the compression side, we have the compression steel strain. But when I am defining a beam with tension steel at 0.005 or greater strain, when concrete will crush, I will get the neutral axis depth just like I got for singly beam, that C will be equal to 3 over 8D. So you can also derive this equation from the above strain diagram. You will get same answer as you got for singly beam. And then A will be beta 1 3 over 8D because A is beta 1C. Now when I will substitute A with this particular A, which is corresponding to 0.005 strain in the tension steel, I am allowed then to put a subscript over here, that it means in a doubly beam, this will correspond to a row which is satisfying the row max conditions, because we have considered that subscript max in a way that that is the maximum allowed reinforcement ratio, which will give us 0.005 strain on the tension side. In order to differentiate it from the singly beam, I will put a bar on top of it. So this bar will tell us that we are actually talking about a doubly beam. So when I substitute A over here and I rearrange my terms, I will get cancellation of D. And then when I examine the first component, it is exactly the rho max equation which we derived for singly beam. So it means I can then replace it with rho max of singly plus rho prime. So it means rho max of doubly beam is simply the summation of rho max of singly plus rho prime. And don't forget, in this equation, by default, you are assuming that when steel on the tension side it is at 0.005, steel on the compression side also yield it. So it is like case one. But suppose if it is not yielded, then it means with your rho prime, you will always get Fs prime, because it means compression steel is below yield stress. Then when you divide this Fs prime with Fy, which we have done division in the third step over here, so it means from that step onward, you will always get Fs prime over Fy with rho prime in case it is case 2 WB. But it is important to note that even if it is case 2 doubly beam, Fs prime over Fy will always be less than 1. Qualitatively, I am talking about. And maximum value of this ratio will be 1 when compression steel will be at yield. So even if it is case 2 doubly beam, your second component will be reduced. So it means the rho max of the case 2 doubly beam will be lower, or the reinforcement ratio will be lower than the rho max of case 1 doubly beam. So I can you can say assume at this stage that even if I have the case 2 doubly beam and in my assessment stage I have no exact idea that what will be Fs prime, it will be close to Fy or 50% of Fy, but I can get a hint that if it finally will be a case 2 doubly beam, my rho max will be further less. So in this way, in my classification, I need to be little careful. But since in the next slides, I'm going to discuss the case 1 and case 2 assessment based on row. So this will become a open secret, because we will know that what is the status of compression steel by calculating one row value. So at this stage, you can assume that for both case 1 and case 2, your equation will be rho max plus rho prime for case 1, and for case 2, rho max plus rho prime into fs prime over fy. Now in making the classification, idea is same. The cross section given has the area of tension steel, calculate that area of tension steel, divide it with B into D effective area, get row of your equation, row of your section, then calculate row max of doubly beam from this equation. So when you have the row max in hand and you know the row of the given cross section, if rho is equal to or less than rho max, you will be confident to state that this doubly beam is actually tension controlled under reinforced, and its steel will excessively yield when finally failure will take place. So it is a ductile doubly beam. And if it is not actually less than, then actually you enter in the either in the transition domain or maybe in the over reinforced domain. That will be decided if you know the row balanced of the doubly beam. So this row bar balanced is another threshold which will help you to classify that your beam is in the transition domain. Now for driving the row bar balanced, again the idea is same. There is absolutely no difference. I will call the longitudinal equilibrium equation like I did earlier, and I have two components. I will expand them, I will substitute them, I will assume compression steel at yield, and I will divide both sides with FYBD, and I will replace AS over BD with rho, AS prime over BD with rho prime, and I will get the same equation which I got on the previous slide. Now this, from this equation onward, decision will be made that what A I want over here. So I will refer to the strain diagram, and now in strain diagram I want A of my choice. You know very well that balanced reinforced beam means when concrete will crush, steel is at yield. And again in balance reinforced cross sections, don't forget tension steel is the criteria, that concrete on tension side and compression concrete will approach their limiting strain simultaneously. We are silent about the compression steel. Compression steel status does not change the balance reinforced requirement. For balance reinforced means tension steel and extreme fiber on the compression side, which is of concrete. And when you derive this C, you get the same answer as we got in case of singly beam. It was 600 over 600 plus Fy into D, and A will be beta 1 into C. So this AB you already have derived in your singly beams. So once you put this A over here, you are allowed then to put a subscript, and to distinguish it from singly beam equation, you will put a bar on top of it, and in this way again you will rearrange the terms when you will substitute A with AB, and you will be having cancellation of D and D. And once you rearrange the first component, it is interesting to note that our first component on the right hand side is row balanced of singly beam. So it means row balanced of doubly beam is equal to row balanced of singly beam plus rho prime. Even in this equation, the same ambiguity is there, that what is the status of compression steel. If it is case 1 doubly beam, it means compression steel at yield, then this equation is valid. If this will be a case 2 doubly beam which is balanced reinforced, then this Fs prime over Fy will be present along with a rho prime. So, but keep in mind that this ratio will be less than 1. So it will further reduce the second component, and rho balanced of case 2 doubly beam will be lower than rho balanced of case 1 doubly beam. So in this way, qualitatively, we can discuss, but since I said we know in advance what is the state case 1 or case 2 beam, as on the next slide we are going to derive that equation, so we can confidently write equation in start that whether we will put Fs prime over Fy along with that, or we will keep it 1 because compression is also at yield. Now the range is quite clear to us. If our given cross section rho is greater than rho max but is less than rho balanced, we are in the transition domain and phi will be interpolated just like we did in case of singly beam, that phi of this doubly beam will range between 0.9 to 0.65. If by chance our rho comes out to be exactly equal to rho balanced, again phi will be 0.65 because on balanced failure phi is still, the capacity reduction factor is still 0.65. And if suppose rho comes out to be greater than rho bar balanced, it means we are in the over reinforced domain, which is highly unacceptable because that beam will be brittle in failure, and even in doubly beams we can't allow such uh, beams which are giving us little or no warning. Now, important definition, but important row which I want to derive is row CY. As we are talking about case 1 or case 2, again I will start with the same uh, longitudinal equilibrium equation T equal to C. Up to this stage, there is no change in the steps which we have performed on slide number 2 and 3. A over here now, since yes, one important point is now over here I'm not saying I am assuming Fy, because now I am actually working on a case 1 doubly beam rho estimation. So it means I am actually looking at that doubly beam in which compression steel is at yield. So that is why I am not putting a circle which I did in the previous slides and I mentioned assume. Now actually it is the case 1 and I want to make sure that when compression is at yield, what will be the rho value. So I have this equation with me, and A over here now will decide what neutral axis depth I'm going to put. So I am now using the strain diagram above neutral axis. So I'm using the similar triangles ADE and triangle ABC. So when I will divide DE with AD equal to BC with AB, and I will perform some steps and I will bring the C on one side, I will get this equation from similar triangles ABC and ADE. And furthermore, if you want to memorize in terms of stress, so you can multiply this equation with ES over ES, its numerator and denominator. So ES 200,000, when it will be multiplied with 0.003, it will become 600 over 600 minus Fy into D prime. So A is actually beta 1C. So when beta 1 will be multiplied, you will get this uniform stress block depth. Keep in mind that there is a minus sign over here. This is a very common mistake made by students, that they, by mistake, when writing this rho CY equation, they forget that there is a minus sign over here. So just like in doubly beams, there is a plus sign. Here by derivation, when you will perform steps, you will get negative sign over here. So when you will replace A with this A and you will rearrange the terms, you will get finally the equation with these components 0.85 beta 1 Fc prime over Fy. Now d prime over d will remain within the equation. They are not cancelling. And furthermore, there is a 600 over 600 minus Fy. Don't forget this minus. And then this equation is available for us. We can calculate this rho Cy. And don't forget, if in the cross section your rho is greater than or minimum equal to rho Cy, then compression steel will yield. If it will not be greater than or minimum equal to rho Cy, then it will be case 2 doubly beam. So now for classification of your doubly beams, you have three equations with you: rho max, rho balanced, and rho Cy. Now I will suggest you that the problem which I solved in the recorded video, which was the case 2 doubly beam analysis, I have given you a cross section 300 by 300 with 4 number 25 bars on the tension side and 2 number 19 bars on the compression side. Concrete grade was 20 and steel grade was 300. Perform the classification of that beam, calculating rho and rho Cy and rho balanced, and then classify without going into detailed analysis that whether it is case 1 doubly beam, case 2 doubly beam, whether it is tension controlled doubly beam or transition controlled doubly beam. So now you have the required uh, assessment tools with you, which are different rho equations. So from that discussion on rho, now I want to discuss design of doubly beams. So don't forget that to design a doubly beam is a little straightforward flow chart, and you need to follow that flow chart in order to get to the right design value. If you will not follow the flow chart which I'm going to discuss today, you will not be able to successfully complete the design in minimum time. So don't forget the steps which I am going to discuss today, and there is one example problem which I will also discuss in this online lecture. So just like other design problems as a structural engineer, when you will be asked to design the beam, you will be given with the architectural working drawings. That's it. Architect will tell you about the dimensions of the room sizes, about the story heights, permissible clear story height. He may have some concern on the beam depths. So he may point out that don't go beyond this much depth below the slab. So because for HVAC ducting, heating, ventilation, air conditioning ducts, due to some provision of false ceiling and requirement of clear story height, there might be some concern on the beam drop below the slab. So architectural depth restriction is very common because architect will be on the driving seat and he has actually interviewed the client and he knows the requirement of the client as well as finally what will be the uh, overall uh, clearance which will be required in the building. The requirements of the building system will be his actually headache to fulfill. And our requirement is that if there is some depth restriction, can I still design a singly beam with D greater than D minimum? If I calculate the D minimum, which we did for singly reinforced ductile beams, if my D allowed is not greater than or equal to that minimum required depth, then obviously either will I will go for a over reinforcingly beam or transition reinforcingly beam, or I should switch to a ductile doubly beam. So obviously I will not be allowed to go for over reinforced singly beam. I will then have to deal with I will prefer to design a shallow doubly beam. And Once you are given with the architecture working drawings and you decide what type of slabs will be, whether they are one-way slabs or two-way slabs, depending upon the aspect ratio, and finally you decide the provision of beams, whether beams will be only present on the column center lines, or you will also provide some beams, secondary beams, and you will divide the big panels into smaller ones. So all this will be actually your uh, responsibility. As a structural engineer, you have to uh, decide the structural system, that whether it will be slab system one way or two way, whether you will go with the primary beams only, or on the primary beams you will put some secondary beams, and primary beams will act as spandrel beams for the secondary beams. So if this working will be done, and now you know that finally the slab system is two way, then you will calculate the load transfer path. You will divide the slab into trapezoids and triangles, and you will transfer the load on the beams. If they are along the longer span, two trapezoids will contribute their load. If they are edge beams, one trapezoid will contribute load. If the beams are along the shorter span and they are interior beams, two triangle will contribute load. And if the beam is on the edge and it is running along the shorter span, one triangle will contribute its load. Also, you will get idea whether cantilevers are present or not on the edges, and their load will also be distributed. If on the stem beam some wall is present, that you will get idea from architecture working drawings, that where are the walls present. So if walls are directly riding on the beam, you will add their loads as well. So in this way, loads and span length is actually your uh, part of job. You have to actually estimate the loads, and the you know from the architecture working drawings what are the spans. Then as a structural engineer, you have to intelligently select the concrete grade for that project, the steel grade, and you know modus of elasticity of materials, or you will be performing some test in the laboratory. You will engage some testing laboratory to get the modus of elasticities, and as well as verification test for the concrete and steel specimens. So in this way, this data will be with you once you start doing calculations for the project. Furthermore, as I earlier said, depth restriction given by the architect. Now, when you have all this data with you, then obviously you will decide the width of the beam. Decision about the width of the beam also needs the information that where you will rest your beams, what are the column dimensions, available formwork. So normally in Pakistan, we start from 228 millimeter, 9-inch wide beams, then one fit 300 millimeter, and then maybe multiple of 75, 375, 15-inch, 18-inch. In this way, we decide the B value. More H will reduce the deflections, and it will help us to go for single beam design. But as I said, if there are some depth restrictions, then you will calculate the center of the tension steel from top fiber and center of the compression steel from top compression fiber. And then obviously the gross H you will estimate. And for the design of doubly beam, you have to design two steels, tension steel and compression steel. And then finally you will draw the cross sections and longitudinal sections. So detailing will be provided. Now there are few steps which I which I suggest you to memorize them and practice at home, so that you can successfully perform the design of doubly beam. First thing is calculate all type of loads acting on the structure, and hence calculate the total factored load. I earlier discussed that this is your part of job. Then calculate the total maximum factored movement MU acting on the member. So just suppose that you are asked to design a beam which is single span and it is also simply supported. So just one academic problem, that you have a beam of 6 meter span and you got the calculation of WU on that beam, obviously if beam is simply supported, it is single span, your maximum movement will be WL square by 8, and that you will get of that beam. Then if you have that MU with you, you know that you will decide the FC prime, you will fix the B, and you will calculate the D minimum against that demand of MU. If calculate the minimum effective depth required for singly reinforced section, which I have shown you on slide number 7, if the available effective depth is lesser than the minimum, it means architectural restrictions are that you have to finish your beam in 300 millimeters, suppose total H and gross depth, and subtracting cover of 75 millimeter from it, you will be left with sorry 65, suppose 65 millimeter from it. Like I'm actually taking the example problem. So 300 was the total depth, 65 was the cover, so you will be left with 235 D. But your calculation from this equation tells you that your D minimum should be 450, and then furthermore when you add cover in it, you will get to 525. So you actually require 525, but architectural restrictions are that please finish it within the 300 millimeter maximum from top to the bottom. So if this is the restriction, then don't forget, you can't violate the serviceability requirements. That serviceability H you still need to fulfill, because otherwise this beam will give you offensive sag. Deflections, immediate deflections will cross the permissible. So you need to uh, check carefully that even in doubly beams, serviceability will still govern. And if all is well, you have the serviceability checks okay, but the minimum check is not okay, then the design will be done as doubly reinforced section. It means if you will still go singly, you will end up with a over reinforced probably singly beam, or maybe in the transition domain. But for a new design, we prefer to go for the ductile beam, tension controlled under reinforced. So if this situation comes, design the member as doubly member if your D is less than D minimum. So once this is the situation arised, then from this bullet onward, we are now actually following step by step the doubly beam design procedure. What you will do, step 1 is calculate the maximum movement that can be resisted by the tension steel according to the maximum steel ratio for singly reinforced section for an extreme tensile strain of 0.005. So this is the first step. What you will do, you will write the rho equation of singly, rho max equation, and you know that it is 0.85 beta 1 into 3 over 8 into Fc prime over Fy. From this rho max, multiply that rho max with the B of the cross section and with the D which was allowed by the architect. Maximum permissible effective depth, which obviously is less than D minimum required for singly. So you are using rho max of singly, and you are using the allowed effective area B into D, and in this way what area you will get, you will call it AS1. AS1 means that area of steel which is based on the rho max of singly, and if This is the area of steel based on rho max of singly. It means the uniform stress block depth of this cross section, which has the area of steel equal to rho max of singly, will be beta 1 3 over 8d, because we know that when 0.005 versus 0.005 will be the strain diagram, neutral axis will be at 3 over 8d c, and a will be beta 1 3 over 8d. So it means I actually want to calculate that based on rho max area of steel, which will be definitely at yield because it has the A beta 1 3 over 8D, will and will get definitely 5.9. This cross section, which although is shallow, but I am calculating rho max steel for that section, and based on that area, how much movement I can generate, resisting movement I can generate. I will put a subscript with that as 1. So that M1 is actually based on AS1, and AS1 is based on rho max. Obviously this M1 will be less than your demand, which is MU, because if it will be equal to MU, it means you are actually having a singly beam capacity, and singly beam capacity is equal to your capacity, which is demand. Even though you reduce the D, it is impossible to definitely M1 will be some magnitude out of the total required. So what you will do then, in the above expression, M1 is the amount of capacity provided by the maximum compression in concrete, which is CC, and AS1 is the area of tension steel to balance that CC. I may call it T1, the tension force developed by the steel, which is AS1, developed in the concrete according to the code allowed value of extreme tension strain, which is actually 0.005. So based on this, I will get one couple between steel and concrete. Now, in reality, my MU is greater than M1. And what will be the surplus movement, which I am unable to resist by making only couple between steel and concrete? That will be M2. That M2 I will then equate, and I will write one equation now between a couple between steel and steel. So I will say the surplus movement I will be resisting with the compression steel and the component of tension steel. So what I will do, I will write equation between a compression steel AS prime Fy and one component of tension steel which will make equilibrium with that. So this M2 and the lever arm, you know that between steel and steel we discussed in the previous lecture, will be D minus D prime. So CS into lever arm, or T2 into lever arm, which is D minus D prime, and putting along with that phi as well, into phi as well, will be equated with the surplus movement M2. So above one is the force equation, and this one is actually the movement equation, right? Sigma M equal to 0, and it is the internal couple between steel and steel. So in this equation, you will see I am rephrasing it, that I am bringing AS prime on one side and I am keeping M2 on the, which was on the right hand side as in numerator, and I am bringing phi Fy d minus d prime in the denominator. At this stage, you will have one question in your mind that what I did, I assumed that Fs prime is equal to Fy. So I am actually making this equation with the condition that it is a case 1 doubly beam. I am assuming that the compression steel is at yield. So that is the reason I am using in the denominator Fy. Suppose if your compression steel is not yielding and it is case 2 doubly beam, it means Fy will drop to Fs prime, and what will happen on As prime when Fy will drop to Fs prime, your As prime will get bigger because the denominator will reduce and area of steel will increase. So if the compression steel is not yielding, in order to generate that force, you need to increase the area. So that is what will happen if finally you will end up with design of case 2 WB. But at the moment, assume, and we want to check it later on, that whether our assumption was right or wrong in making the design choice. So I am using As prime, and based on that, I am using Fy, and based on that, I am calculating As prime. And what As prime I got, I will make it, I will call this As prime that it is actually As with subscript 2. Earlier I got As1, now I got As prime, and that As prime I am replacing it, or I'm just calling it that it is equal to actually As2. On the compression side, it is As prime. The same amount of area of steel I will also add on the tension side, because earlier As1 was making couple with concrete. Now the surplus movement will be made, will be resisted by a couple between steel and steel. So the amount of area steel As prime, when once I add on the compression side, the same amount of area of steel I will add on the tension side. So the total tension steel will then be As1 plus As2. But don't forget, in this calculation of As prime, we assume that the compression steel is at yield. So the total amount of tension steel may be calculated by adding extra amount of tension steel equal to the above required compression steel into the already calculated tension steel, which is done over here. Now the stage comes to check that whether our assumption of compression steel yield is right or wrong. So what I will do, now I will call the rho Cy equation, and I will calculate the rho Cy. And I will compare it with the calculated rho, because now I have As, and As over Bd will give me rho. I will compare this rho with rho Cy. If it is greater than rho Cy, my design is complete and I need not to change anything. What I assumed, I got the same answer, and I will finally sketch on compression side As prime, on tension side As. My design is over. Just I need to sketch. But if it comes out to be not greater than or equal to rho Cy, then it means my compression steel was not yielding. It is at Fs prime. Now I want to do some adjustment because I am little underestimating the compression steel. There is important information here. Since you are adding As prime also on the tension side and you are calling it As2, although you checked and you got that your rho tells you that your compression steel does not yield, and now you need to revise As prime, this revision will be only done, only and only done on the compression side. The tension side area steel, what you added as As2, will get yield because your A calculated was based on rho max and whatever you add on the tension side will get yield. However, whatever adjustment now you will make will only be on the compression side. So what is explained over here, that if rho is not, if greater than or equal to rho Cy, compression steel is yielding and design is over. If steel is less than, compression steel is not yielding, so stress in the compression steel is determined then from strain compatibility. To calculate that if it is not yielding, then how much is the stress in the compression steel, you will call the same equation based on strain compatibility. And A you all earlier has calculated, it's beta 1 3 over 8D. From that A you will get what is Fs prime. Obviously it will be less than Fy because your rho is less than rho Cy. Now from this Fs prime, we will do a little revision. What that revision will be, my AS prime trial, which I earlier calculated, and I got impression it is not yielding against my assumption. I need to little enhance that area steel. How I will enhance it? By multiplying it with the ratio of Fy over Fs prime. So the amount of drop in force, I will compensate by multiplying it with the ratio of Fy over Fs prime. Because I assume, suppose it is 420 grade steel, I assume that steel is at yield. So I assumed it is at 420. But once I checked later on, I got the idea that steel is at 300. So it means I am thinking that AS trial is Fy, but actually AS trial is at Fs prime. So both can't be equal. They can only become equal if I will increase the area of steel. AS double prime into lower stress may become equal to AS prime at Fy. So this, how I will get to this AS double prime, I will multiply it with the ratio of Fy over Fs prime. So in this way, I will get a revised area of steel. And as I said earlier, don't do this revision on the tension side. On the tension side, earlier calculated Fs prime is the right answer. So now let me apply this discussion to one example problem. So if you agree, I can continue discussion on the design problem. If you need a break, because some students last time pointed out, but I suggest you that allow me to finish the lecture, because on my side, I have no guarantee that the light will remain, you can say, functional. There are many times power shortages. So if during lecture the power failure will occur, then we will waste time. It is up to you. If you want to take a break, I can stop for 5 to 10 minutes, or otherwise I can continue. What you suggest?
Continue.
Good. So we have a design problem here, which is very simple and straightforward design, which will help you to understand the flow chart what I discussed. In this example problem, there are two cases, case 1 and case 2. Case 1 actually is the derivation. It is not actually the direct design. It is just one tricky question, which is to derive and satisfy this equation. So I will not discuss this in this online lecture. So, but its solution is present, and you can go through it, and some the good students obviously will enjoy that tricky problem. But I want to discuss a field problem, that if you are in design office and you want to design a doubly beam, and to design a doubly beam, if this second question with the condition is given, area of compression steel is minimum. The flow chart, which what I discussed, is actually fulfilling this condition that area of compression steel is minimum. So even if I do not put this restriction, by default, the flow chart what we discussed will give you the answer which will fulfill the second condition. So you can simply uh, get a statement: design a simply supported rectangular beam having a span of 6 meter, subjected to a total factor load including self weight of 70 kilonewton per meter. Now there is one point which is important. This is a kind of academic problem that we are giving you span and factor loads. As I said earlier, in practical life, nobody will tell you such kind of dimensions or loading. It will be your actually uh, responsibility or your job to get the loading and to get the dimensions. Obviously, you can discuss with the architect regarding some spacing of the columns. You might have your concerns if spans are large, but finally, you will have to get to the values. You obviously will ask architect about the floor finish thicknesses, type of floor finish, type of building, so as to select appropriate live loads, structural use. But finally, the drawings and other information with cross sections will be provided to you with some architectural restrictions. And then finally, you will get to such spans and loads. And don't forget that when beams are having some cross sections, when you estimate the load transferred on the beam, we did that estimation in the last lectures, and we divided the slab into trapezoids or triangles. What we were calculating was the weight of the slab only. What was the slab dimension, and what we did the calculation, that does not include the stem load, the projection of the beam below the slab. It also carries some weight, and that can also be calculated by multiplying with the cross-sectional area the density of concrete. So when you will multiply with the cross-sectional area the density of the concrete, I may call it rho d, which is 2400 kg per meter cube, it will then give me answer in kg per meter. I can multiply this with the 9.81 divided by 1000 to get in kilonewton per meter the self weight of the beam. Then I can multiply it with 1.2 to factor this self weight, and I can calculate the ultimate self weight of the beam. That will also be added in the beam line load, which we earlier calculated based on the slab load, or if there is some wall directly constructed along the stem of the beam, that will also be included. So don't forget, not only slab load, self weight, floor finish loads, wall loads, stem load of the beam need also to be considered. It may vary from 3 to 5 kilonewton per meter depending upon the depth of the beam, but it carries some weight. They are not very lightweight stems. If the concrete is normal density concrete, it will carry definitely some appreciable self weight which must be included. So in this problem, we are directly telling you that whatever is provided to you, it includes the overall load, which is including self weight or whatever the uh, slab loads are. You need not to further even amplify it because the given is total factored load. So it is already factorized, right? Now, it is further stated, depth of the beam should not exceed its span by 12. So this gives you a hint that if in statement question is that try to finish your beam within a span by 12 height, it means 6 over 12, 6000 over 12. That gives us one reflection that there are chances that if my D minimum will exceed this given H, because from this H, obviously I will subtract the cover and I will get the D value. Suppose I assume the cover 75, so it means H minus 75 will give me the allowed effective depth from the architect. Now, if my D minimum will be less than this D, I will be happy. I am having singly beam. But if my D, allowed D, comes out to be greater than, sorry, if my allowed D comes out to be greater than D minimum, I must be happy because my allowed effective depth is more than minimum required to get the singly beam. But if the D minimum of singly comes out to be greater than my allowed depth, then I will be in trouble because it means I am getting into the unpreferred domains if I still go singly, or otherwise I should go for the doubly beam. Although in this problem, it seems span by 12 is such a uh, relaxing edge because span by 12 will definitely fulfill the serviceability requirements. If you check the serviceability table shared with you chapter 9 of ACI 318 2019 publication, you will get idea that span by 12 envelop all the end conditions and almost all the steel grades except cantilever beams. So in this way, if it is simply supported beam, I have no concern about serviceability. So the architect depth restriction fulfills directly or indirectly the serviceability, but I am little concerned about the minimum required for the singly beam. So I need to then check that in the solution of the problem. Furthermore, it is given by the questioner, which will be actually your part of job to decide the width of the beam. Here in this problem, they are fixing the B, it is 1 foot, and also giving you the concrete strength, which will be your part of job in practical life, and the steel grade. So both are given to you. So it is just kind of a simple academic problem that each and everything is provided to you with the intent that finally all the students will get more or less the same answer. If I will leave it to you that every student will have its own choice of concrete and steel grade and different B values, so everyone will then get a different answer depending on the materials grades or effective widths, depths. So that is the reason we normally fix the condition so that all the students try to get the same answer. Because in design, no, normally you will not get one answer, but if your approach is right, your concept is right, you will get the maximum marks. Unless you make some stupid mistake, then definitely marks will be deducted. Now, note, keeping the maximum tension steel ratio uh, rho max, the amount of compression steel will be minimum. As I said earlier, that this condition the will be fulfilled automatically with the flow chart which I have discussed. So when I am starting with the rho max of singly, by default, you will get this promise that your compression steel will be minimum and it will be actually a economical WB because your area of compression steel will be reduced. Now, what I explained in the flow chart, I am going to repeat those steps. Given data is span, load, width of the beam. Furthermore, questioner is fixing the effective depth of the compression steel. I may say D prime for the compression steel. So it is not leaving to you to decide suppose it is fixed in the statement that the compression steel from top compression fiber support is at 58 millimeter. Actually, conditions for the compression steel are also same, that minimum cover mandatory for the compression steel is also as per code 40 millimeter. Then if you assume, sorry, then if you assume that your, which will be our next topic, shear design of beams. So you assume that the ties which are enveloping the longitudinal steel are of dia 10 millimeter, it will become 50. Then you assume that the bar, which is top bar compression steel, has the dia 16. It means half of that will be 8. So in this way, what they are assuming, that the cover to the center of the top steel, based on assumption that top steel might be number 16, they have fixed 58. So normally you might be little conscious in your selection, that if I will finally end up with the steel area which is larger than 16, so I need to be little careful in selecting the D prime. So if you assume it will be number 19, so half of 19, or number 20, half of 20 will be 10. So it means it will increase to 60 millimeter, just 2 millimeter more. But in this problem, suppose we propose you that for compression steel use 58, and what about tension steel? For tension steel, things are also are more or less same. If a layer is single, what I will have further ties enveloping the steel, so I will have 40 plus 10 plus I will add the distance from uh, the half of the dia of the first layer. So in this way, I may get 65 or 60 or 75. If I will end up with two layers, then obviously I need to calculate the center of the layers, and I may get more uh, cover from soffit to the center of the steel layers. So in this way, I need to calculate that. So here, what they are saying, assume depth of centroid of the compression steel from the extreme compression phase 58, Fy, Fc given, allowed by the architect is 500, span by 12, H max allowed, and it is important to note that H minimum for deflection criteria, which is serviceability requirement, which we can't violate, is span by 16. So I am satisfied that architect is not asking me for something which is unacceptable, because serviceability is very important. Otherwise, the deflections, immediate deflections will increase, and a sagging system will not be a preferred choice in design. So I'm little satisfied that 500 is well above the restriction of deflection. But now let's find out that what about the D minimum for singly. Here again, H selected by the architect is 500, and as well I selected, suppose I assumed the cover for the tension steel, which I said on the previous slide, that this, suppose in this problem we are assuming it is 75. So in this way I will subtract from 575. So D permitted by architect actually is 425 if cover is 75. Agreed? Then what I have a demand 70, span and conditions were simply spotted. So I selected the coefficient 1 over 8, and I got the ultimate movement, maximum movement at the mid span, which will be maximum for simply spotted beam 315. I used it with the FC prime and the B value. Just give me 1 second. जी सरवर, जी सरवर मैं क्लास में हूँ जी प्लीज सर। जी अस्सलाम वालेकुम, मैं क्लास में हूँ जी, बात करेंगे जी जी। हाँ मैं अवेलेबल, मैं आ जाऊँ। ओके ओके sorry. So when I substituted 315 into 10 power 6 mu in Newton millimeter and then divided with the megapascal in megapascal FC prime and B in millimeters, I am little surprised because what D required is 506. Further, when I will add cover in it of 75, it will exceed the H allowed by the architect. Even if I compare it with the architect's permission, I am little lower in the permission. So it means I should not be then designing it as singly, since my D allowed is less than the minimum. So I should go for a doubly reinforced section. So these are the initial steps which are to be done if in the statement questioner is silent. If questioner will in start ask you, which will never be in practical life actually, that someone will ask you, architect or client, that please design a doubly beam, because client or architect, they have no idea about doubly beam. So if the in question paper someone asks you that design a doubly beam, it means he's trying to give you a hint that's right in beginning, go for the doubly beam design. But otherwise, if the question is silent regarding that hint, then you have to go through these checks, and then finally after making these steps you will announce that I am going for the doubly beam design because my allowed D is less than the D minimum required for singly beam. So I am just skipping the case 1, so please go through it at your home. I am will discuss in detail the case 2. So are you still uh, in good energy? May I continue?
Yes, sir.
Good. Okay. Now, when you have the row max, I said earlier, there is a typical flow chart for doubly beam, and now I'm going to follow it step by step. Very simple and straightforward. First, what I will do, I will call the row max of singly. And based on row max of singly, I got the row value. And I multiplied that row max with the effective area. Here I am selecting the D allowed by the architect, which is permissible. And I got a S1. And since I am using row max, I am allowed to use the uniform stress block depth corresponding to the row max of singly beam. And I got the A value. I am calling the movement equation because I am using rho max based on that area steel calculated A. I am allowed to use 5.9 and I got the capacity of that section, which will make a couple between steel and concrete, a value 222.3 kilonewton meter. But sadly, my demand was 315. So I have a surplus movement which is about almost 93 kilonewton meter above my requirement, above my capacity, which I can generate with AS1. So this surplus movement, I will try to get that additional capacity by making a couple between steel and steel. So in making this couple, I am assuming that compression steel is at yield and the lever arm between them D minus D prime. Lever arm between steel and concrete was D minus A by 2 and between steel and steel is D minus D prime. And I got the AS prime additional steel on the compression side and the same amount of steel I must add on the tension side to get my total tension steel. And I mentioned you in my previous half of lecture that this AS what you will calculate is the final answer that will not be changed even if compression steel is not yielded. So this what you got AS is final, absolutely final. Now it is the time to check that my assumption of compression steel at yield is right or wrong. So I have the A with me because I used rho max to calculate AS1 and whatever additionally I am adding up, that is actually making a separate couple between steel and steel. So when I use this A and I call the strain compatibility equation Fs prime, what we have derived in the previous lectures, I got the information that my compression steel is little below the yield limit. Yield limit was 420, but it is almost at 381 megapascal. So theoretically speaking, I was wrong in calculating the AS, in announcing that AS prime is at Fy. So the amount of mistake or amount of error was that I used AS prime Fs Fy, but it was actually AS prime Fs prime. So what I can do is I can't make it yield, but what I can do is I can get the same amount of force what I require because on the tension side this AS2 whatever was added on the tension side it will be yielded. But on the compression side, this AS prime, what was calculated, is not yielding. How I can make them equal? I can make them equal by increasing the area of steel. In this way, force will become equal. How much I will increase? Intelligently, I will multiply that area of steel with this ratio. This ratio will help me to enhance that much area, which will finally give me the force equal to T2. And T2, I told you that whatever you will add on the tension side, it will start yielding because earlier your calculated was rho equal to rho max. So in this way, little enhancement is done and your revised compression steel area is now from 668, it increased to 737. And this is now final. What you earlier calculated 325 plus 320 on the tension side will remain same. There will not be any change. The only change you made is on the compression side and you made it 737 rather than 668. But on the tension side, you are not doing any correction. It is 2313. Obviously, when you will consult the nominal bar tables, you will find that nominal areas may not be exactly equal to the theoretically calculated. You need to do little round up. While doing round up, don't round up to a larger extent. Within 1 to 2%, try to finish the selection. Now, as a matter of fact, some students may have argument now at this stage that when I look at this sketch tells me that the top bars, if my 40 is the mandatory cover, 10 millimeters is the tie, and I have 320 bars on the tops on my selection. So theoretically speaking, in my actual section, which will be executed at site, mechanically speaking, my cover is 60. Do you agree with my comment? 40 plus 10 plus half of number 20. Are you there?
Yes, sir.
Okay. ये आप सिर्फ सीआरई ने जवाब देना होता है, बाकी कोई सबके माइक बंद हैं या कि बाकी भी पार्टिसिपेट कर रहे हैं?
Sir, I'm not CR.
Okay. Okay. Good. It means के सीआर किधर है इस वक्त? Let me just exit. मैं जरा आप लोगों की presence check. 33 students are online. So all the 32 or 33, let me download. जी कोई अपना माइक जरा माइक तो अपने ऑन करें. अभी जो मुझे जवाब दे रहे थे ये कौन से स्टूडेंट थे?
Sir, Hassan Ali.
हसन अली. लेट मी चेक. रोल नंबर क्या आपका?
Sir, 71. 2018 CIB 71.
गुड. तो 71 हसन. सीआर किधर है इस वक्त? है इस वक्त ऑनलाइन? मोइन है इस वक्त, नवीद है.
यस सर.
ओके सीआर आप भी फॉलो कर रहे हैं सारे
यस सर.
गुड. एंड ये उजैर हैं आप? उजैर शफीक.
यस सर.
ओके ओके. और कौन है इस वक्त जो बड़ा अटेंटिव है? अनीस मलिक.
यस सर. मोहम्मद अचाम हियर.
गुड.
यस सर. आई एम हियर.
ओके ओके. एंड माय पॉइंट वाज, लेट मी गो बैक टू दैट.
Yes, sir.
जी मैं जो बात करना चाह रहा हूँ, लेट मी री write that cover. So we started this problem with the assumption that our cover is 58 on the compression steel. Now I'm talking about a very practical, you can say, check that when you finally sketch, your sketch will be executed at site, not your calculations. So sketch will be your language actually at site. So a structural engineer will talk with his sketch, and finally your drawing will be executed at site. So what you did in your calculations, that was you assume that your top bar has the compression steel has the cover 58. Agreed? That we assumed and we started the discussion onward. But now when I finally sketched, I selected 3 number 20. My cover is 40 mandatory from code, 1.5 inch or almost 40. My ties to envelop, we will discuss this in the coming lecture, shear design of beams. These ties are actually arresting the shear cracks, and they are actually providing us the resistance against shear failure. So this tie, if it has 10 millimeter dia, so distance consumed by this tie will be 10, 40 cover. I selected a bar, 20 dia, half of it will be 10. So mechanically, in my sketch actually, the cover is 60. You agree with that? And furthermore, code has the direction that if you will go for 2 layers, gap between the 2 layers to allow the aggregate to flow through and to get a good bond and to envelop the bars for gripping within the concrete, you must have a clear space between 2 layers not less than 25 millimeter. So what you are selecting 325 in first layer, 320 in second layer. So mechanically speaking, I have a 40 cover. If my tie is 10, then I have the 25 millimeter lower layer. And if I assume my center of the steel layers will be right in the middle, although it will be little lower, because when I will calculate y bar by this equation, that area of steel in first layer and its distance from bottom plus area of steel in second layer plus its center distance into its distance of center of the steel from bottom divided by total steel AS1 plus AS2, I can calculate what is the center of the steel. Can you help me to calculate 325? We are using actually standard US bars, standard SI bars. तो 325 की बनेगी जी 3 इंटू ये स्टैंडर्ड जो स्टैंडर्ड एसआई बार्स का नॉमिनल एरिया 5 होता है, यूएस कस्टमरी का 500 होता है, यूएस कस्टमरी का 510 है, इनका 500 और 20 का 3 इंटू वो चेक करके बताएं, ये 400 है. प्लीज चेक एंड लेट मी नो. Into y1 of the first will be 50 plus 40 plus 10 plus half of 25 by 2 to get the center of the layer from the bottom. So how much it will be? 62.5. So the first layer will have the distance from the soffit 52.5. Second layer 3 into 400. Please check ये जो number 20 का standard SI bars का क्या है area, and its distance from center will be 40 plus 10 plus 25 plus 25 plus half of 20. So 40 plus 10 plus 25 plus 25 plus half of 20, it is 10. So it is 50, 60, 70, 75, 100, 110. Agreed? Divided by plus Please open your mics and tell me the answer of the center of the steel from the bottom, because we have taken 75 millimeter in our calculations.
Sir, I think it's 300 area जो 20 number bar का है.
Sorry, 284 है ना उसका, 300. Oh, sorry, yes, you are right. जी, चूंकि जो 19 का 284 है, so I replaced it with 400 with 300. Now please calculate. जी, आप बताएं, how much is the y bar? डिस्टेंस मैंने सही निकाला है, 62.5 पहली लेयर का, सेंटर से बॉटम का। मैं दो लेयर्स का जो क्लियर गैप है वो 25 1 इंच रखा है मैंने, which is normally code will ask you the largest bar dia 25 millimeter or the coarsest particles size. तो आप नॉर्मली ये जब आप 3/4 इंच डाउन कोर्स एग्रीगेट यूज करेंगे, उसको अगर आप 33% बढ़ाते भी हैं, 1.33 से मल्टीप्लाई करते हैं, तो 1 इंच नॉर्मली गवर्न करेगा with the dia 25 or with the coarsest particle 3/4 inch in the concrete. तो दो लेयर्स के दरमियान का गैप प्लस getting to the center of the top layer will give us y2, which is calculated here, and this is y1. जी, अब बताएं।
Sir, 80.31.
Good. 80.31.
31.
Let it be 80.5. वैसे 80.31 को आप एग्जैक्टली तो फील्ड में 80.31 ही होना है, क्योंकि ये आपने एक इनको फिजिकली नीचे स्पेसर दे के इस स्टील बार्स को ऊपर उठाना है। नॉर्मली हम मोटर के ब्लॉक्स बनवाते हैं, बास जो जगह हैं बास प्रोजेक्ट्स में बहुत ही जो गलत प्रैक्टिस है, दैट दे यूज ब्रिक ballast or some broken pieces of brick, clay brick, to lift up the cage. You know that the brick is the porous material, it sucks water, so it will trigger the rusting of the steel bars. It is also having less density than concrete, so it is not recommended to lift up the cage by putting the brick pieces under the steel cage. तो आपने जब फॉर्म वर्क में इसको स्टील केज को उठाना है, तो आप इसके नीचे मोटर के ब्लॉक्स बनवाएंगे 40-40 मिलीमीटर के थिक, और उनके ऊपर जाके ये स्टील केज रखेंगे. अदरवाइज देयर आर सम अदर मैकेनिकल मेजर्स, बट डोंट यूज ए मटेरियल which is porous, which is flexible, and which has less density than concrete. And furthermore, in some projects people use marble pieces. तो जब फॉर्म वर्क खुलता है तो नीचे मार्बल के चिप्स नज़र आते हैं, मुख्तलिफ चंक्स. तो ये चीज़ें सारी फिर आपके नेगेटिव मार्क्स में जाती है, नेगेटिव वर्कमैनशिप के. यू आर नॉट फॉलोइंग द राइट approach. Good field approach is to be careful in lifting up the cage, and don't compromise on cover, otherwise your bond and your resistance against fire and protection against rusting will be compromised. जी, अब आपने 80.5 या 80.31 आपने मुझे बताया. Now I need your comment. आपका जो डिजाइन है वो तो हुआ है 75 पर नीचे का कवर और ऊपर का 58 पर. इस पे आपकी सारी कैलकुलेशन है. आप लेआउट करवाने चले हैं फील्ड में 60 वर्सेस 80.31. Now this is your assignment, homework, to do the reverse engineering and solve this beam and determine its capacity. You have to solve this beam on the similar lines which I discussed in case of an example problem solved in class with 425 on tension, 219 on compression, and we got the capacity. Now you will do the capacity analysis, and if your MU will be with this actual sketch 80.31 and 60 of the top bars, which are the, and use the actual nominal areas 3 number 20, because little rounding up is done, your calculated values are not exactly in agreement with the theoretical. So your theoretical were 2313 and 737. So you did a round up. So for example, ये कितना आपका आता है AS जो टेंशन स्टील है 325 के 3 into 500 plus 3 into 300. So how much you get? AS 900 plus 1500. Uh, 3 into 500, 1500. 3 into 3, 900. 2400 against 2313. So you require 2313, but because of the available nominal areas, you selected 2400. You required 737 and you provided 320. So it is almost 900 against 737. So my question to you is, although you have dropped the lever arm by having in actual sketch more covers, so when you will increase the covers from 58 to 60 and from 75 to 80.31, so you are actually reducing the lever arms. But on the other hand, you are also increasing the area. So overall, what capacity now you will get in actual beam which will be executed at site, that I want to know. That in your beam at site, which is of 6 meter span and has simply supported end conditions, and it has this cross section, how much MU and then finally how much WU you will get. If your WU comes out to be greater than 70 kilonewton or equal to 70 kilonewton per meter, I will be satisfied that my design is okay and I have case 2 doubly beam in which tension steel is still at yield and I have the phi, whether it is in the transition domain or in the tension controlled under reinforced domain. So what phi you will get. So please attempt this problem at home and then let me know. It is your assignment and please upload it within the files folder section B to let me know what capacity you get. Now this will give you a good confidence कि आप ही की डिजाइंड बीम जो एग्जीक्यूट होनी है फील्ड में उसकी किसी ने वेट किया है, उसको किसी ने रिव्यू किया है और उसकी कैपेसिटी निकाली है और वो आपको बताता है नहीं जी आपको तो 70 किलो न्यूटन पर मीटर चाहिए थी, आपकी बीम की तो आ रही है जी 68 किलो न्यूटन पर मीटर, या वो आपको कहता है जी आपको 70 चाहिए थी एंड यू आर गेटिंग 75 72, so you are fine, you are even above the demand, so your design is a so this is how we do vetting और कैपेसिटी एनालिसिस कि हमें एक सेक्शन दिया जाता है और उसकी हमें कैपेसिटी निकालनी होती है। तो अभी आपने एक डिज़ाइन किया है और उसी की आप खुद कैपेसिटी निकालोगे तो आपको अपॉर्चुनिटी मिल रही है दोनों काम करने की। So in next lecture I will talk about the shear design of which is this one, and then finally we will discuss continuous beams and then bar bending schedule. So let me escape. Let me stop recording. So this recorded lecture is being uploaded. Now please let me know how many of you have understood today's lecture. हाथ खड़े करें. When I say raise your hand, सारे हाथ खड़े करेंगे और जब हम क्वेश्चन पूछेंगे तो सारे गुड, वेरी गुड, वंडरफुल, माशाल्लाह. इसका मतलब है कि सब ने समझ नहीं, अभी आस्ते आस्ते खड़े कर रहे हैं हाथ जी. गुड गुड. हाथ खड़े करने में आप बहुत माहिर हैं. आई फील सेक्शन बी इस मामले में काफ़ी ओबीडियंट है, लेकिन आपने काइंडली गो थ्रू दिस एग्जाम्पल. अभी नहीं खड़ा किया है मोइन अवैस और नवीद अब्बास और शाहिद शाहजेब एंड उजैर, ये नहीं है सो ऑनलाइन. अयान, मोइन अवैस, नहीं समझ आई इसको. ये 2018 और 2017 सिविल 290. आर यू गेटिंग 290? प्लीज ओपन योर माइक. 290 ये री रजिस्ट्रेशन है.
Yes, sir. Yes, sir.
Good.
I got it.
Good. So please attempt the question at home, the analysis problem, and then please upload. तो अगली दफा सीआर आपको मुझे याद करवाना है कि ये क्वेश्चन हम 1 आवर के लेक्चर में पहले इस क्वेश्चन को जो आपने अटेम्प्ट किया है उसको डिस्कस करेंगे.
Okay, sir.
Okay, so may I exit the meeting, or if you have any question you are welcome. If no question then I can exit. Okay then, Allah Hafiz.